And thank you to everyone for joining us today. My name is Ajay Kulkarni. I'm the co-founder CEO of Timescale, and I'm here to talk about something that I think is actually a pretty fun question, which is, what the heck is time series data? For some of you out there, maybe new to time series data, I think you'll find this talk quite informative. But even for those of you who may be familiar or think you're familiar with time series data, I think you'll find this talk very interesting because you'll find that we may in fact challenge you to think about time series data differently than you might be thinking about it before. So first, who are we? Timescale. We're the developers of an open source time series database that supports full SQL, and this is a database that's actually has already been downloaded over 1 million times with thousands of production deployments, and we secured over $31 million in funding. And at a broad picture, what we do is empower organizations to leverage the power of time series data to analyze the past, understand the present, and predict the future. And some of these organizations include the ones listed on the screen, but also folks like yourself. And then one more thing before we kick off into the main topic is first a quick thank you to the City of New York. This talk is part of New York City Open Data Week, so big thank you to the Mayor's Office for teaming up with us on this talk, and also welcome to those of you joining us as part of New York City Open Data Week. So back to our main question. What the heck is time series data? So to answer that question, let's start off with this picture. And the question is, what do these 5 things have in common? We have, a pseudo self-autonomous vehicle by Tesla. We have autonomous trading algorithms on Wall Street. We have a smart home device. We have, the Amazon, and really our same day, shipping and delivery network, and the open data from the City of New York. One thing you'll find is that when you look at all these things, it's like, wow, like they're kind of all signs that our world is changing faster and faster than we've even seen before. But number 2, if you look at these workloads, they actually have something else in common, and is that each of these things are actually monitoring change. So with this car, a car is constantly monitoring how the environment around it is changing in order to make smart driving decisions. A trading algorithm is making decisions on how the market is changing to make intelligent trading decisions. A smart home device is monitoring how your home is changing in order to respond to cues and different behaviors in an intelligent way. These really robust shipping and delivery systems that are so great that I think today we even take like same-day delivery for granted. What they essentially do is they track how packages are moving, they're changing their location through the supply network. And the 4th thing is when you look at the City of New York and open data, the city's actually made available a lot of data on how, for example, New York City police cars and even taxi vehicles are moving throughout the city. And what you'll find is that when you go into all these use cases, they're not only are they monitoring change, but they're essentially tracking time series data to monitor that change. And that's kind of the theme, I think, of this talk. Seeing time series data in all these use cases is actually kind of an interesting thing, because originally time series was just a niche market. If you think about where time series came from, it primarily came from the finance industry, and it wasn't, in finance, it wasn't even trading algorithms. It was just like storing stock prices over time, right? And then you had, the rise of DevOps and monitoring data and time series within that, where you had businesses who are monitoring their servers, the CPU, memory, and even like high level things like power consumption. But what we found is that in the last 2 years, time series data has exploded from a niche workload to the fastest growing category in that 2-year period. And there are actually quite a few reasons for this, but we think there's actually one main driver, and that driver is the rise of machines. And this is actually something that I think most people haven't realized, but that in the past 2 years, the number of machines connected to the internet, and these are excluding smartphones and excluding traditional computers and servers, in the past 2 years, the number of connected machines has already surpassed the number of human beings on this planet. And if you look at this graph, you can see that we're really good at producing new machines and we're actually relatively slow at producing new human beings. So this gap is only widening. And in fact, this also means that with the rise of machine data, and machines generate far more data than human beings do. And these are, all these data points essentially speak to like the volume of data that machines generate. And so what essentially has happened is that you have machines generating more data than human beings, and they already outnumber us. And so this time series data, and that's essentially led to the rise of time series data. Because of this trend, time series has now become a workload that's ubiquitous, that's everywhere. So not just finance and DevOps, but also in factories and industrial machines, or in energy and utilities, or transportation logistics systems, or even web and mobile eventing data. As people monitor, as consumers use their apps and kind of websites, but also this new frontier of AI and machine learning inferences relies very heavily, on time series data. Now, you may ask, okay, that's great. Time series data is everywhere. Okay, I've convinced you, but still, like, what is time series data? And to answer that question, we have this illustration. So in this illustration, you have 3 sources of data. You have a building, a very New York City looking building. You have a farm, and you have a factory. And maybe at time 0, all 3 of these sources are sending sensor data. So it might be temperature data, humidity data, uptime, occupancy, but a variety of sensor data. And at time 1, there's another row of sensor data. At time 3 and 4, more sensor data. And over time, as you can see, what we're essentially building is a time series data set. Now, what's really interesting about this workload is that as every new data point comes in, there's something we're not doing. And what we're not doing is we're not overwriting the old row. What we are doing is that when a new data point comes in, we're writing it as a new row, as a new row, as a new row. And this is really, the hallmark of time series data, is that you end up recording every data point as a new entry. Or in fact, put another way, you rely heavily on inserts and not updates. Here's another example that may also provide more context to what is time series data. This is a data set from the city of New York. This is New York City taxi cab rides for the first few seconds of 2018. We tried to get 2019 data, but I don't think they've published it yet. But what you see in this data set is that for each row you have a taxi cab pickup, drop off, total fare at the end of the drop-off, number of passengers, and a trip distance. There's actually a lot more columns in it. It's a really fascinating data set. And then you have, another taxi cab ride, another taxi cab ride. And again, over time, every time there's a new taxi cab ride, what this data set is doing is not, overriding the existing record, but essentially adding more records and more records and more records. And by doing that, we can see not just the current state of the world, like not just, where are all the taxi cabs today, or what was their most recent ride, but we can see how our world is changing. So in other words, how are taxi cabs changing? How are their rides changing throughout the day? How are they moving throughout the city? And so this actually leads us to I think our first definition of time series data is that time series data is data that collectively represents how a system, process, or behavior changes over time. And in fact, this notion of analyzing changing is quite powerful, because capturing change over time completely transforms our view of data. If in the past, if you're just looking at one data point, you just see the current state of the world. But capturing change over time lets you see not just the data point, but a line. Not just a still image, but a movie. And essentially, this actually allows you to see trends of how things are happening. Now, and we'll actually come back to this topic, in a few minutes. But like, one question you might have now, if I were in your shoes, one question I would have right now is, great, okay, I think I have a handle of time series data, but but why should I use a time series database? There are a lot of databases out there. You're probably using, several of them right now. Why do I need yet another database for this workload? And it really comes down to scale. If you think about, what we just talked about, relying heavily on inserts on updates, you'll find that time series data piles up very quickly. Again, here, every new record is a new row. And in fact, because it piles up very quickly, you end up having scalability problems when time series data workloads sooner than you would with, say, a traditional workload. And these scalability problems on a traditional database means that you typically have to, maybe you buy bigger machines or more machines or more memory, but that actually becomes very expensive very quickly. In contrast to that, what time series databases have done is that they've introduced efficiencies by treating time as a first-class citizen. What kind of efficiencies? Well, it's kind of provide a bit more context or kind of, explain, how a time series database could do this. We're going to talk about a topic that's actually very close, that we're quite familiar with, which is timescale. What we essentially realize is that time series data is actually easily partitionable. You can partition it in one direction by time, but another direction by space. And by space, we need any kind of hash partitioning key. It could be a device ID, a user ID, a customer ID. In fact, you can have any number of these. And then what we essentially do is we say that okay, now you have your data, and it's kind of subdivided into these n-dimensional chunks. Which are essentially subtables. And each of these chunks, we then right size them so the most recent chunks fit in memory. What that allows us to do is something that we call automatic space-time partitioning. So that when data comes in, as a new tuple comes in, it automatically gets routed to the appropriate chunk, and new chunks are created as necessary. Now, what you end up having is data that's highly partitioned, in some cases over thousands or tens of thousands of chunks, yet what we do is we treat that as a single table and essentially hide all that partitioning behind this abstraction layer called a hypertable. And what this hypertable does is actually something quite powerful, is that it says that, hey, even though your data is now heavily partitioned for performance reasons in all these chunks, you can access it as if it's in one single continuous virtual table. And in fact, this hypertable performs just like a vanilla, it's a normal Postgres table. So you can, create, indexes, triggers, constraint, foreign keys, upserts, you do upserts, you can actually manage, the table, you can manage the schema as if it was a standard Postgres table. When Timescale initially launched 2 years ago, in the first few months, this is essentially was our primary innovation and kind of what I think people found it very fascinating. But of course, we've done a lot of work since then. And to highlight, one of the things we developed since then is I wanted to talk about another type of optimization that we've done, more recently, and this is actually a really powerful feature that we call data reordering. Data reordering essentially, says that, look, we know that, you might write your data in a certain way, for example, by time, but you may need to query it in a different way, for example, by device. And you see this a lot, for example, in IoT. What reordering does is that, after the data has been written, it essentially rewrites that same data in a different format on disk. That is more in line with how you're going to access the data. And what we found is that this, and this is a command you can run manually, or that you can create a policy such that it runs automatically behind the scenes, and that and we found that the effects of data reordering, often leads to query performance improvements in almost like 1,000 times faster queries. So what essentially shown you is that, okay, here is how time series databases in general can optimize for time series data, and by showing you how Timescale, how we did that. Now, creating these, optimizing your database in these ways introduce efficiencies like we discussed earlier. What kind of efficiencies? Well, you can typically see, given the same computing resources, see higher insert rates. You can see faster queries. You can see lower total cost of ownership, and in fact, you'll have an easier to use database. And again, to illustrate, what kinds of efficiencies you can expect, we're going to talk a bit about, what efficiencies you see with Timescale. So number one, versus say a traditional relational database like Postgres, we see 20x higher inserts at scale, but we also see faster queries, and in some cases, we see 10 times faster queries that are time ordered, and in fact, we even see 2,000 times faster deletes. Versus a NoSQL database like Cassandra, which are typically known for scale, which is typically known for scale and scalability, we still see 10x higher inserts, but again, we see anywhere from some cases 2 to 44x, at other cases over 1,000 times faster queries, again because we have optimized for time series data. Cassandra is in particular very interesting because we've actually done a pretty thorough TCO, total cost of ownership analysis, where we found that Timescale, we had 3 Timescale nodes, outperformed a 30 node Cassandra cluster, in this case, 38% higher inserts, but at 1/10 the cost. So first, this shows you how Timescale compares against Cassandra, but this is also an example of how when you use a time series database, the types of, in this example, TCO benefits you can get by being able to get more out of your existing kind of computing resources. And in particular, the way we've optimized Timescale for time series data has also allowed us to even outperform other time series databases. For example, InfluxDB, where, as we show here, we found that Timescale has higher inserts for most workloads than Influx, and in fact, there are quite a few other differences. In particular, the query language, where we support full SQL, and they've had to create their own, kind of proprietary, bespoke query language. And there are actually quite a few other differences that we capture in detail in this blog post that's linked below. It's actually a pretty hefty 6,000 word blog post. So we've talked about some of the efficiencies you see with these first 3 bullets, but again, let's also talk about the 4th bullet, which is how does this introduce kind of ease of use efficiencies. With Timescale, what we've done is by focusing on time series data, it's allowed us to prioritize our product roadmap on analytical functions that are quite common in time series, and where you have it's actually a pretty simple one that normal Postgres just does not support, as an example, where in the top half of your screen you have kind of raw noisy data, but look, you may want to, you probably want to aggregate the noisy data into, say, 5-minute intervals. And that's what the bottom half is doing, essentially saying, okay, we kind of organize it using an average over 5-minute intervals, but this is actually where but then it gets even more interesting, where let's say you now say, okay, well, I also have this missing data, how do I fill it? Well, one way you might fill that gap is just a simple linear interpolation using the last average, and this is something that we make it really easy in Timescale to do. Another way you may want to fill that data is you may want to say, oh, I actually don't want to interpolate. I just want to take the last value that I saw and carry it forward, and then I will, and then when I get the next value, I'll just move the latest value. That's called the last object carried forward, and that's another type of analytical capability that we've added to Timescale because we focus on time series data. And kind of, maybe a third one I want to talk about is around automated, data retention. And this again, kind of touches on not just ease of use, but also the scalability challenge you have in time series data, where the data piles up very quickly. One way to solve this problem is you say, okay, maybe your data has a certain shelf life, and after a certain period of time, you may want to ETL data, out of your database into, maybe a different, archival store, or maybe you just want to delete your data. And we've made it, quite easy to, manually, delete data, or even to set a policy with which the database will automatically delete data, once it reaches a certain age. So, to kind of summarize kind of this section of the talk, okay, I think I know what time series data is. Why should I use a time series database? Again, it comes down to, 4 main reasons: higher insert rates, faster queries, lower total cost of ownership, and an easier to use database. So something we've done so far is I think we've touched on not just the nature of time series data, but also Timescale. So I thought I might take a few minutes just to talk about a little bit more about Timescale, and actually answer the question. It's like, okay, if I want to use a time series database for my time series data, why should I use Timescale? Well, before Timescale existed, there were essentially, only, two options to store your time series data. Option A, you had databases that didn't scale. These are your classic, relational databases that were easy to use, supported full SQL, quite reliable, huge ecosystem, but were hard to scale. Which is why you had the rise of option B, which were, non-relational systems that scaled, but at a cost, right? And the cost was that they siloed your data, and they sacrifice your performance. Why do they silo your data? Because they essentially, force you to put your time series data in a NoSQL database, but then your relational data, or your metadata that describes the time series data in a separate, probably SQL database. But then they even sacrifice performance, and they sacrifice performance because a lot of these databases, because they're written from scratch and they totally, threw away the relational model. A lot of them don't support, I think basic database fundamentals like compound indexes, secondary indexes, and as a result, they also underperform. They may perform well on your primary query or simple queries, but they end up underperforming on complex queries and end up becoming harder to use. So those are essentially the two options that we faced when we were building Timescale. And in contrast, we wanted something that combined the best of both worlds. We wanted something that actually provided SQL but also scaled, and that's essentially why we built Timescale, to create the first open source time series database that supported full SQL. And when I say full SQL, it's actually, I think, worth drilling deeper a little bit into why we think full SQL is so important. Well, it's fundamentally, SQL is actually a fairly well-known query language. According to Stack Overflow, it's the fourth most popular in programming scripting or markup language, and the first three are JavaScript, HTML, and CSS. But even if you look on LinkedIn, if you just search for SQL, you get 9.5 million results, for SQL related, people and companies. While if you search for NoSQL, you get, quite a few, a lot fewer than that. In fact, we're seeing 90x more results on LinkedIn. And what this essentially means is that by adopting a database that for time series data that supports full SQL, that actually introduces a few advantages. The first advantage is that if you already know SQL, if you're amongst that, 57, 60% of the people who know SQL, then there's no learning curve really to using Timescale. And in fact, and probably even more critically, there's no organizational retraining, because most likely, people in your company already know SQL, or they're using tools that already speak SQL, either internal tools that have been built, or maybe third-party tools like visualization tools or other connectors. And then number three is that as you're growing your company, choosing a database for time series data that supports full SQL makes it even easier to hire for expertise, because 60% of your total pool already knows SQL, as opposed to some kind of NoSQL language. Because of this approach, this actually allowed us to create a time series database that unifies time series data with business data, and so that you have not just the time series data that's coming from your sensors or your assets or your systems or applications, but you also have the business data, the business relational data that describes essentially those sources of time series data. So it may be device metadata, maybe metadata about an application or about a customer, about a site, and we also allow you to unify this with geospatial data. And geospatial data may be an actual location for an edge device. It may be a moving location for a moving device for asset tracking. Because of this unification, this also allows us to simplify your stack, to essentially take something where in the past you would have had maybe one database for relational data, another database for time series data. With Timescale, you can actually unite them into one database. So instead of in the older world, maybe you had to do complex join logic at the application layer. With Timescale, you can do all your joins at the database layer, through like a SQL join, and it leads to a much simpler stack and much simpler, application logic. Timescale is also a database that can scale up and down with you. So it can scale, scale up to the cloud, and we've been deployed on, on public clouds and private data centers, in single node and clustered fashions. But we also scale down to, the edge, where the edge might be on-premise, an on-premise hefty machine, like, like a crazy supercomputer, or like a server, or like the edge, which could just be like a Raspberry Pi. And Timescale has been deployed successfully in this whole spectrum of scenarios. Also, because of our approach, Timescale is engineered on top of Postgres, and we're packaged as a Postgres extension. This allows us to inherit the rock solid reliability of Postgres, which has been developed over 20, 30 years of development. And the way we essentially do this is we essentially live alongside standard kind of Postgres data, such that standard SQL queries are routed directly to Postgres, but while time series queries are routed to essentially Timescale, and then we handle them. And in fact, and we can obviously join across those two different types of data. But also because of our architecture on top of Postgres and our reliance on SQL, ever since Timescale launched, we've been able to launch with the largest ecosystem of tools, of compatible tools. These include visualization tools like Power BI or Tableau or Grafana, or data infrastructure tools like a Kafka or a Spark, or even other types of services as well. And one thing we really like to point out is that one of the advantages of Timescale and by having the largest ecosystem is that not only can it be the right solution for your use case today, but it actually can extend to fit your needs as your needs grow and as they change over time. And that's essentially what we've built so far with Timescale, but there's even more to come this year, which I will not talk about in this talk, but I'm sure we'll have more webinars in the pipeline that'll mention this, that'll talk in detail about these three areas. Number one, we're developing a variety of enterprise features, enterprise capabilities. We are launching a fully managed version of Timescale in the public clouds, and we're launching essentially the 2.0 version of clustering, which will support fully scale-out clustering across multiple nodes. So before we go, I thought I would leave with essentially one parting thought, and this parting thought is kind of based on our experience with Timescale. When we launched the product, about 2 years ago, we thought we were solving an interesting problem, and we felt there was a need for it, essentially a time series database that scaled but supported SQL. And the response, to be perfectly honest, was even larger than we expected. And right away we found that, wow, like this problem is actually a lot bigger than we expected, and we're like, wow, like what might be going on? And so now it's been 2 years that we've been in this business, and we've come to a conclusion that that the time series industry is exploding. Time series data is exploding because the data industry as a whole is actually undergoing a generational shift, a once in a generation shift. And you think about the history of the data industry, you had maybe the first generation, you had, the relational database era in the 1970s through 1990s for, traditional transactional processing. And these are, maybe, Oracle, your DB2 SQL Server, and even some, open source databases like Postgres and MySQL. But then we even had, in the 2000s, in 2010, we had the rise of the big data and non-relational systems, primarily for analytics. And this, we saw the rise of Hadoop and Cassandra and Mongo, and obviously every other kind of non-relational system. And I think what's remarkable about this era is that, these technologies were developed, in large part because of the rise of the internet. And what the internet did is that it created a new source of human-generated data that vastly surpassed the data we had generated, previous to that, data in the form of new, web pages, blog posts, e-commerce transaction, events, and these technologies were developed because the prior technologies at the time, this initial generation just couldn't keep up with this scale. What we've found is that, today we're entering essentially a new era, and it's a new era that, for lack of a better term, is even bigger than big data. It's even bigger because if you, as you recall, the big data era was thanks to the rise of human data. But what now we're seeing is something that's thanks to the rise of machine data, and machines generating far more data than human beings. But there's also an even like another trend that's happening that's kind of creating this generational shift is that the nature of the data we're collecting is in fact evolving. And it's evolving in this way, where maybe in the past, maybe in the 1970s to 1990s, what databases would do is store, maybe the current state of something. So it'd store, the current balance of Ajay's bank account, right? And then maybe the big data era, what the databases started storing was every state of something. So, how is Ajay's bank balance changing over time? So, i.e., bank transactions. Where we're heading now is that, as computing becomes more powerful and as storage gets cheaper, businesses are now naturally storing data at a higher resolution. So now what we're doing is we're storing everything as this timestamp data point, is every user event, application event, service event. In other words, is that as computing evolves and as our business needs become more real time, we just naturally start storing data at higher and higher fidelities. And in fact, what we believe is that time series data, is growing not just because the rise of machine data, but because in fact, time series data is the highest fidelity of data that we can capture. And I mentioned this earlier, but I'm going to touch upon it one more time. Is that what this fidelity lets us do is that look at not just points, but essentially lines, and not just still images, but essentially watch the movie of what's happening in our businesses and in our organizations. And if you think about this, and if you kind of go down this line of thought, it actually, I think, leads to a really interesting place, which is this question, which is, in fact, is all data time series data? And this, this question first occurred to us, about 2 years ago when we launched the company, and we thought it was kind of outlandish at the time, but since then, it's actually, we've thought about it and we're like, this actually kind of makes sense. Because if you think about it, every data point is a timestamp, and in fact, storing each data point with its timestamp actually allows you to analyze trends over time. And in fact, we would argue that not storing your data in the time series format is actually throwing away valuable information, because you're throwing away that knowledge of how your data set is changing over time. And so, and you can see this, the effect of moving to time series in these examples. And I'm just going to touch on the last one because I think it's probably the most provocative one. Is that even in like a SaaS application, maybe you're tracking your total users or total, total active users, but what if instead you tracked, maybe total, user events over time or logins over time, and you move it to time series format, you end up getting, what you end up happening is end up getting a higher granularity of what's happening in your business, and I would say greater insight. As a final thought and a final slide, I'll leave with this notion is that you probably have time series data today, have more time series data today, and you don't even realize it. And in fact, as you think about, back to our original question, what the heck is time series data, and how you may want to store it, I would challenge you, and I would challenge you not just to think about the time series data you think you already have, but also challenge you to think about the related data sets that are analytical in nature, that would actually, but that would benefit the business by being stored in a time series format. And with that, I'm gonna wrap up, and we'll go to questions. And Lindsay has just given me a list of questions that the folks have entered in. Let me start with some of the broader ones. So I think the first question is, what is the future of time series data? I think I touched upon this a little bit towards the end of the slide, but end of the presentation. But I would essentially speak to it in two ways. I think number one, time series is something, if the trends continue, and right now they're showing no signs of slowing down, time series has only become more and more ubiquitous, and we're going to see it not just within, DevOps and finance and IoT, but also, in mobile eventing, AI, ML, and so I think, number one, it's going to become ubiquitous. But I think number two, and I think that where it gets really interesting, is that what we'll end up finding is that more and more analytical workloads I think will naturally migrate to the raw time series format. And in fact, what you'll find is that the future of time series data is in particular it's also a migration from a more of a traditional kind of data warehouse data. Question two, what industry is positioned to generate the greatest amount of time series data? That's a great question. It's hard for me to say what's going to generate the greatest amount, but I can share what we see today of, in terms of industries generating large amounts. Obviously you have, industrial data within, say, manufacturing, oil and gas, utilities that generate a large amount of, time series data. You have the whole, logistics industry, and by logistics I include not just, traditional, trucking and asset tracking, but also the next wave of autonomous vehicles and autonomous trucking. And there you have not just time series data, but I'd say time series plus geospatial data, so geotemporal data. But I think there are a lot of other industries that are we're probably a little early for them right now, but we're starting to see them, in particular healthcare, as an area that already has a lot of time series data. But given the sensitivity of the data, I think are slower adopters, are slower, adopters of time series, of the time series format. But yeah, I think we'll see more of that in the next few years. And the third question we have are, what are the implications of not treating your time series data as first class data? Well, I think if you mean this from the context of a database, the implication is that if you're using a database that does not treat time series data as a first class citizen, you're going to end up needing to spend more money on more resources. So either bigger boxes, more servers, or more memory in order just to handle the volume of data you're getting. It'll also be I think clunkier to use because you won't have the type of capabilities that that we showed. But I think kind of more broadly speaking is that if you don't think about time series data in general, I think what you end up doing is you end up throwing away valuable information, kind of like what we discussed earlier, is that every data point has a timestamp, and by storing your data in a time series format, this essentially allows you to see how your data is changing, and not storing it in the time series format, you end up throwing away that change data. Question 4 is, what is Timescale's single greatest differentiator? I would say we have quite a few differentiators, but I'll recap them, very quickly for the benefit of the person who asked this question. I would say number 1 is the fact that we support full SQL, and the benefit of SQL is the ones that we've listed here. Number 2 is that we unify time series data with relational data and geospatial data, which is something that no one else does. In fact, these first 2 things, no one else does full SQL and business data. Number 3, we can scale up and down with you, so that there are some time series databases or time series services that only exist in the cloud, or only exist in a clustered fashion. And there's some that exist on the edge, but they don't operate in a cloud, or they don't cluster. And Timescale is something that can scale up and down with you. We offer the rock solid reliability of Postgres, and in fact, we would argue that thanks to Postgres, Timescale is the most reliable. And this is actually what our users have found as well. We're the most reliable time series database. And the last differentiator I would say is that because of our approach of embracing Postgres and SQL, we're the time series database with the largest ecosystem, and in fact, we can grow with you as your application grows. And I think we have one last question: is how can I learn more about time series data? Well, that's a great question. We have a blog, blog.timescale.com, where we talk more about time series data. And in fact, there is a blog version of this talk that's on there as well that may go into deeper detail. It actually has the same title. What the heck is time series data? But in general, if you do have questions about time series data, why to use a time series database, or even more specifically, how TimescaleDB might be able to fit your needs, we're available for those questions. Feel free to email us. You can actually email me directly at ajay@timescale.com, or you can email our general support at support@timescale.com. And we also have a pretty active Slack community where you can sign up at slack.timescale.com. And one more thing is, in fact, we have one more webinar in just 1 week from today, and the title of the webinar is Analyzing a Real-World Time Series Data Set with the latest TimescaleDB features. That's going to be led by one of our our core engineers. Well, thank you again for joining. And again, if you do have any questions or we can be of any help, please don't hesitate to reach out. Thank you. Bye.